In this video, we're going to talk about the binomial distribution. It's one of the discrete numeric probability distributions that's very important. And this is a new version of this video. A very helpful Berkey Academy viewer pointed out that I had typed this combinations formula wrong here, so I decided I would just re-record the whole video. So the binomial distribution, the name binomial comes from the fact that we're doing some kind of experiment. And at the end of the experiment, there are only two things that can happen. So bi for two and nom for name. And so the binomial distribution says, at the end of this experiment, we're either going to say that we got a certain result or we didn't. So those are the only two outcomes. Either something happened we were looking for, or it didn't happen. And so the technical bullet points for when you're looking at a binomial distribution, it's used when you're repeating the same thing again and again and again. And each of these same things we're doing is called a trial. A trial could be flipping a coin, could be rolling a die, but it has to be doing the exact same thing repeatedly. So rolling a die 5 times or flipping a coin 10 times, for example. Each trial is identical and independent of each other. So each thing you're doing has to be the same. The probabilities can't be changing. And each thing you're doing has to be statistically independent of the other time you're doing it. So each time I flip a coin, the last time I flip the coin cannot affect the probability of getting a heads the next time I flip the coin. And that's certainly true of coins, so we don't have to worry about that. At least with coins or with dice. But you don't want to use the binomial distribution in a case of, say, cards. If you're dealing 5 cards from a deck, each time you deal a card, you're changing the probabilities depending on what cards have already been dealt. So each trial is identical and independent. Each trial is described as either a success or a failure. So that's where this binomial, two names, comes in. You have to define what is a success, and everything else is going to be a failure. So a concrete example. Suppose getting a 6 on a die is a success. So I'm going to roll a die. If I get a 6, it's a success. Anything else is a failure. Now, if we were just rolling a die one time, we can talk about the probabilities pretty easily. If I roll a die one time, the probability of getting a success is 1 out of 6. The probability of a failure is 5 out of 6, because 5 of the faces of the die are not a 6. The binomial distribution is useful when you're doing something repeatedly. So instead of rolling one die, I'm going to roll a die 5 times, or I'm going to roll 5 die all at the same time, 5 dice all at the same time. So I might want to know, what are my chances that I can get a 6 on exactly 2 of 5 dice? This is the kind of problem the binomial distribution was invented to handle. Here's the binomial formula. It looks kind of ugly when you first see it, but there are really only 3 things that you need to find to stick into this formula. The binomial formula gives you the probability. So the 3 things here are x, n, and p. By filling in n, x, and p, you get the probability of getting exactly x successes. In n trials, you're doing the same thing n times. What's the probability that x of them are successes? And p is the probability of getting a success on exactly 1 of these trials. So we already can fill in from thinking about these 3 things we're looking for. Let's reread this question. What are my chances that I can get a 6 on exactly 2 of 5 dice? Well, how many successes are we looking for? 2. So x is 2. In trials, how many identical things are we doing? Oh, we're rolling 5 dice, which are identical. And p, this is probably the hardest thing for most people to understand about the binomial distribution. P is just look at one of the trials. In this case, look at rolling one die. What is the probability I would get a success if I just rolled one die? That's P. So just focus on doing one of the things. Now if we're flipping a coin, P and a success was getting a heads, then P would be 0.5. We're just looking at one coin, not all 10 coins, or in this case we're looking at one die and not all 5 dice. So you just plug in the X, the N, and the P. Now there's one weird looking thing here at the beginning, and if you haven't been exposed to it, let me introduce you to it very quickly. This is called the combinations formula, this little N and X in parentheses here. Let me introduce that to you here briefly. So that first part of the binomial formula is called a combinations formula. And in parentheses, what we're doing here is we're saying out of N things, what is the probability, sorry, not probability, out of N things, how many different ways could we choose 2 things from the group of N? Now in this problem with the dice, we said N is 5 dice and X is 2 successes. What we're calculating here is how many different ways can I pick 2 dice out of 5 dice? A little bit easier way to think about this is suppose you and 4 friends, you had 5 people in a classroom, and 2 people were going to be called up to write their homework questions on the board. Out of 5 students, we're going to pick 2 of them. The combinations formula answers the question, how many different unique groups of 2 students are there that could be selected out of the 5 students? Now this little notation right here with an N over an X with little parentheses around them just tells us that we're doing the combinations formula, and we would read this as N choose X. N choose X. If we put in the 5 and the 2, out of 5 students, how many different groups of 2 are there? We would say the problem is 5 choose 2. And all you do is fill in N factorial. And again, if you're not familiar with factorial, a factorial says take that number and multiply it by 1 less, and then by 1 less, and then by 1 less. Let's do this example problem over here to make this a little more concrete. So over here we have 5 choose 2. On the top is 5 factorial. So what that's going to be is 5 times 4 times 3 times 2 times 1. That's what 5 factorial means. You actually don't have to multiply the last 1 because multiplying by 1 doesn't actually change anything. So the top here is 5 factorial. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So the 5 factorial is 120. 20 times 3, 60 times 2 is 120. Now on the bottom we have 2 different factorial calculations we need to do. 2 factorial is just 2 times 1, which is 2, times 5 minus 2 factorial. Well, 5 minus 2 is 3. 3 factorial is 3 times 2 times 1. But again, we don't have to multiply by the last 1. So on the top here we have 120 divided by 2 times 3 is 6. 6 times 2 is 12. We have 120 divided by 12, and that gives us 10. Again, what's the question this is answering? How many different ways can we choose 2 students out of a group of 5? How many unique groups of 2 are there? 10. Now you can go through and kind of do this by hand, but it gets very tedious to figure out how many unique groups you can have once you get beyond 3 or 4 or 5. Even 5 is can take a little while to figure all of them out. So now that we know what this combinations formula does, it's good to see it done once. what you're normally going to want to do is on your calculator, you don't want to do these by hand because they do get very, very tedious when the numbers get large. You want to find a calculator that has an NCR or an NCX. Sometimes I've seen it on calculators as RCX. NCR key on the calculator. For example, on my Casio calculator here, it's not very expensive. The way to do this would be to calculate 5 choose 2. I put in the number 5 into my calculator, and then I hit the right button for NCR, and then I hit the number 2, and then I hit the equals key. And then that gives me the 10, and it calculates it all for me. Okay, let's get back to our binomial formula problem. So that's just the very first part, but we're going to let the calculator do the heavy lifting on that combinations formula. Now let's do the rest of this calculation, looking at a couple of examples. So back to rolling dice. Now, once again, what we're doing is we're asking the question, what is the probability of getting 2 6s on 5 dice? Exactly 2 6s, not more than 2 6s, or not at least 2 6s. So how many identical things are we doing? We figured that that was 5. We're rolling 5 dice. What is a success? Always think about this and write it down, because this is a way that I see people get turned backwards and not do the binomial formula correctly. A success here is getting a 6. Sometimes it's more confusing than this, and you want to be clear. What is the probability we will get a 6 when we're rolling 1 die? P. Well, that's 1/6. Or we can kind of round that off as approximately equal to 0.167. 16666, but we'll round it off to 0.167 here for convenience. How many successes are we looking for? Well, in this initial problem, we're looking for 2 6s. Exactly. Now, an interesting question is, before we get going, what could X be? X is the number of 6s we could get out of 5 dice. What are the possibilities? When we roll 5 dice, how many 6s could we get? Well, we could get 0 6s, 1, 2, 3, 4, or 5. All 5 dice could be 6s. Those are the only possibilities. So, for example, you can't have a negative number for X, and in this case, you can't have a 6 or a 7 or an 8 for the number of successes, because you're not doing that many things. Okay, let's fill in the blanks here. N is 5, so everywhere we see an N in this formula, we want to put in a 5. So 5 can go up here. Let me open up my little editor here. So we can put a 5 here in my equation editor. And everywhere we see an X, we're going to put a 2. And that's an X right there, so we're going to put a 2. And everywhere we see a P, we're going to put 0.167. So let me fill that in, 0.167. And the exponent we're going to raise that to is the X, so just fill in 2. 1 minus P here. Well, if P is 0.167, P must be 1 minus 0.167, which is going to be 0.833. 0.833. And we're going to raise that to the n minus x power. N is 5, x is 2. 5 minus 2 gives us 3. And so let's close that so we can look at the resulting formula there. So again, this formula will calculate what is the probability of getting exactly 2 6s. So let's figure this out, and then we'll do another couple of examples. So 5 choose 2 we already figured out was 10. So what's the probability of getting 2? It's 10 times 0.167 squared. So 0.167 squared is 0.027889 times, I'm sorry, that's not 1 minus 0.833, the whole thing. 1 minus 0.167 is 0.833. So times 0.833 cubed, 0.833 cubed gives us 0.578 approximately. Now when we multiply all that together, we get .1612. Now if you rounded anything even slightly differently than the way I did in my calculator, your answer will be slightly differently, but don't worry about that. Don't let that hold you back at all. Now, about 16% chance, or about 16% of the time, whenever you roll 5 dice, you're going to get 2 6s. So this formula makes calculating that relatively easy. Let's calculate another couple of probabilities here real quickly. What if I asked you, what's the probability that I could get 0 6s when I roll 5 dice? Pause the video, see if you can set up what is n, what is x, and what is p going to be, and see if you can come up with the answer, and I'll do the same. Okay, I've edited the formula here for rolling a dice, rolling dice 5 times, or rolling 5 dice once. What's the chance you get 0 6s? We fill in 0 for x, but everything else stays the same. The n stays the same, it's 5 dice, n. P stays the same because the probability of getting a 6 is still the same. So x changes. So here we have 5 choose 0. Now if you do this on your calculator, it's going to give you the answer 1. And it's asking, how many ways can I choose no one from a group of 5? Only one way. 0.167 to the 0 is 1. Anything to the 0 power is 1. So all the action happens right here, 0.833 to the 5th power. And so we get the answer about 40% of the time. 40.1% of the time, you'll roll 5 dice, and get no 6s. Let's do one more example to make sure you have it. Calculate the probability of rolling 5 dice and getting 1 6. Pause the video, do it yourself, and then come back and I'll show you the answer. Okay, I get the same answer, and this is an interesting problem. The probability of rolling 5 dice and getting no 6s just so happens to be approximately, now out to many, many decimal places it changes a little bit, but it happens to be approximately the same probability as rolling 5 dice and getting exactly 1 6. And so here x becomes 1. 5 choose 1. How many ways can I choose one thing from a group of 5? 5. Choose the first, the second, the third, the fourth, or the fifth. 0.167 to the 1st power, 0.833 to the 4th power. Now that we've done a couple of these, let me give you a couple of ways to check. This doesn't guarantee that you're doing the right thing, but it helps, I think. In this formula, the binomial formula, one way to double check that you haven't made some kind of mistake is that this 0.167 has to be, when added to this 0.833, the 0.167 and the 0.833 have to add up to 1, right? Because p and 1 minus p have to add up to exactly 1. So that's just a little quick check. The 0.167 is the probability of getting a success, rolling a 6 on one die, just looking at one. The 0.833 is the probability of not rolling a 6. So those two are basically complements. Now another thing to check is that the 1 and the 4 have to add up to the 5. In, we're rolling 5 dice. Out of those 5 dice, 2 things can happen. Either a success or a failure. In this problem, the 1 tells us we're looking for 1 success, 1 6. The 4 tells us we're looking for 4 failures. That's one of the kind of elegant things about the binomial formula is that the 0.167 to the 1st, that's everything dealing with the successes, and the 0.833 to the fourth power is everything dealing with the failures. All right, this video is running kind of long. Let me speed things up a little bit, but I do need to point out a couple of additional things to you. Once we've calculated the probability for 0, 1, and 2 6s, since these are the possibilities right here, that we could get 0, 1, 2, 3, 4, or 5, if someone were to walk up to us right now and ask us, what is the probability that we could get 3 or 4 or 5 6s when rolling 5 dice, in order to find that answer, we just have to add up these three answers, 0.1612, 0.401, and 0.401. And what that's going to tell us is the probability of getting 0 or 1 or 2 6s. So let's add those up. So 0.401 plus 0.401 plus 0.1612, 0.9632. 0.9632. Now we can figure out, we can just see this clearly, the probability of getting 3 or more 6s, 3, 4, or 5, is kind of small. It's only about 3.68%, 0.0368. So that's a trick to using the binomial formula, is if somebody asks you a relatively complicated question, like what's the probability of 3, 4, or 5, try to figure out the way to do the least work to get that answer. Now, another way to get that answer would be to actually calculate this binomial formula, plugging in 3, 4, and 5, and adding those up. But this is a quicker way, given the information we have. All right, real quickly, one more example here. What if somebody said, okay, let's take a bag full of 32 pennies, and this is something I do in my own class. I take a bag full of 32 pennies, 32 coins, I shake them up and I smack them down on the desk, and then we count the heads. If we were to do the binomial formula, what I always do is I count the heads and then I say, okay, what's the probability that that could happen? And so we count up the heads, and how many heads we got is the number of successes. So that's our x. So in this formula, if I take 32 coins and we want to figure out, suppose what happened is x is 15, I put the pennies down, we count 15 heads, what's the probability that happens? We would fill in n equals 32, 32 identical trials, 32 identical coins, at least with identical probabilities. The probability of a success, getting a heads, is 0.5 for just looking at one coin. And x is 15. What could x be? Well, with if we could flip 32 pennies and we could get no heads, or 1, or 2, or 3, or anything all the way up to 32 heads. So this question, suppose we just wanted to know what's the probability of getting 15 heads. We'd do this combinations formula, 32, choose 15. Multiply that result times 0.5 to the 15, that's the p to the x. Multiply that times 1 minus p to the 32 minus 15, the n minus x, 0.5 to the 17. And 32 choose 15 is a large number, 565 million. Times those two probabilities are very small, you end up with a reasonable sounding probability of about 13%. You can flip 32 pennies, the probability you'll get exactly 15 heads is about 13%. Now, a couple of other things you should know is with a binomial distribution, sometimes it's useful to figure out what the average is, or the mean of the distribution is. In this case, all that's saying is n times p, 32 coins, times p, 0.5, equals 16. If you had 36 coins, on average, how many heads do you expect to get? Oh, well, half, 16. That's all that's telling us. The standard deviation of the binomial formula, sometimes is also useful to know. It's the square root of n times p times 1 minus p. Well, what's that going to be in this case? Well, it's going to be the square root of 32 times 0.5 times 1 minus p times 0.5. Now, what you're going to be doing here, the way I think about it as a shortcut, is the first part, 32 times 0.5 is just the 16. Multiply that times a half again, you get 8. So the standard deviation is the square root of 8. And the square root of 8 is about 2.83. What does that mean? Well, to me, a standard deviation always means it's a common distance that your results will be from the mean, a common distance. So what this tells you is when you flip 32 coins, on average 16 of them will be heads, but certainly not all the time will you get 16 heads. Commonly, you'll be about 3 away on either side from 16. So you could get 16, 17, 18, or 19, or 15, 14, 13, or 12. 3 above and below the mean tells you the most likely range, the most common range where you're going to be. And actually what you learn later in statistics is you can use the empirical rule to say that somewhere in the neighborhood of 68% of the time you'll be within one standard deviation. Now you can only do this with the binomial if your n is large enough compared to your p, but in this example 32 coins is plenty. So this video has gotten very long. Let me end here.